All right, and I think we are live for Chegg's Pre-Calculus and Algebra Office Hour. I'm going to give everybody just a few minutes to kind of log in and start gathering those questions that you have that you want us to answer here live today. So bring in those questions, bring in your Chegg Algebra and Pre-Calculus questions. What is pre-calculus and algebra? That's really anything that happens before trigonometry, right? So we're talking functions, we're talking matrices, we're talking conics, we're talking logs, exponentials, factoring, solving equations, graphing equations. All of that stuff falls under this big umbrella of pre-calculus and algebra. So a big hello to everyone who is rolling in right now. Welcome to the live office hours for algebra and pre-calculus, brought to you by Chegg. I'm at Wallace STEM. You probably know me from my accounts on Instagram and TikTok at Wallace STEM, where I take memes and make them about math. So I say come for the memes and stay for the math. For those of you that have joined these live events before, welcome back. We are so excited to have you back today. For those of you that are new, this is your first time. The goal here today is to help you understand pre-calculus and algebra course concepts better. I'm here every week to help you out with those. You can think about this like a virtual office hour. I'm here to help if you have any questions, so don't be shy. Stick them in the chat and I will try and answer them for you today. To kick things off though, I am a big fan of completing the square. So I want to start with that, completing the square problem, just to kind of practice and review the process of completing the square, specifically when it's not equal to a number, but it's just a function that we need to complete the square on. So I might have something like 6x squared minus 24x plus 5. And we want to complete the square on this. What that means is we want to write this as a perfect square plus something else off to the side that is kind of in the way. So first thing we're going to do to complete the square is we need to factor this 6 out of the expression. So we just have a regular x squared. So I'm going to factor out the 6, which is going to leave me with x squared minus 24 divided by 6 is 4x. And we're not going to factor it out of the plus 5. That's going to be our extra leftover that's off to the side. I'm going to actually leave a little space here that's going to allow me to complete the square and finish this off, because this is the piece that we want to become our perfect square. Now, the way we find our perfect square is we're going to take half of this middle number and we're going to square the answer. Half of 4 is 2. And then when I square 2, we get 4. And I didn't write 4, I wrote 2. So let me erase that. We're going to get 4. So I'm going to add 4 inside the parentheses, and I'm going to subtract 4 outside of the parentheses. But I want to be careful because this 4 technically is getting multiplied by the 6 out front. And so we need to also multiply this 4 by 6. Because when we do that, we're going to end up with the 6 out front. And now we've got a perfect square. Square root of x squared is x. Bring down the minus. The square root of 4 is 2. And then all of this stuff left over. 4 times 6 is 24. Plus 5, we got a minus 19. And we've completed the square on this expression. What's nice, the reason we like completing the square so much is because this information tells us quite a bit about the parabola. Specifically, it's going to tell us that the vertex of the parabola is at the point 2, negative 19. And so we know where the vertex of the parabola is at 2, negative 19. And we know that the parabola opens up because this is positive. And so the parabola is going to look something like that. And that's one of the reasons why completing the square is so powerful and useful to us. Hey, for those of you that are logging in, welcome to our live office hour on pre-calculus and algebra. We're getting a lot of great questions already about things like hyperbolas, about things like factoring, and other things, distributing. So let's take a look at some of these concepts and answer your questions. And keep those questions coming in the comments. This is your office hours, so I can only answer your questions if you stick them in the comments. So let's start with a hyperbola question because it really goes well with completing the square. Let's say I've got 2x squared minus 3y squared plus 16x minus, let's do, I don't want to make the numbers too ugly. Let's just do 18y. I might regret that. Equals 25. I don't know. We need a number over there. The way we make this hyperbola into standard form is we're going to group the x's together to be 2x squared plus 16x. We're going to group the y's together to be minus 3y squared plus 18y. And then that's going to be equal to the other side, the 25. We're going to complete the square like we just did on each of these individual pieces with the x's and the y's. So first, just like before, we factor out the 2 that's in front, leaves behind x squared plus 8x. Factor out the negative 3, leaves behind y squared. We're doing y's over here. Y squared plus 9y. Nope. 18 divided by 3 is not 9. 18 divided by 3 is 6. Equals 25. And then we find the number that completes the square by taking half the middle number and square it. Half of 8 is 4. 4 squared is 16. If I add 16 to one side, I'm going to add 16 to the other side. Don't forget, though, it's multiplied by 2. Then half of 6 is 3. 3 squared is 9, so we're going to add 9. If I add 9 to one side, I have to add 9 to the other side. I keep knocking off my eraser. But don't forget that 9 is multiplied by negative 3. And so when I put all of this together, we end up with a 2 times x plus 4 squared minus 3 times y plus 3 squared. And the other side of the equation, which I cannot do in my head, so I'm going to do it on my calculator really quick. 25 plus 32 minus 27 is equal to 30. And so what we can do to finish this off is we want the hyperbola to equal 1. To make it equal to 1, we're going to divide by 30 all the way across. And that's going to give us that standard form of a hyperbola that we're looking for. 2 over 30 reduces to 15. So we have x plus 4 squared minus 3 over 30 reduces to 10. Y plus 3 squared equals 1. And that is our standard form of the hyperbola. We know it's a hyperbola because of the minus that's in the middle. And that's one of the great uses of completing the square. So thank you for that question. We are seeing lots of great questions come in on the chat. Keep those questions coming and we'll keep talking about them. From Instagram, I see a question about the transformation of functions. Let's take a look at how we can transform functions on the coordinate grid and really get an idea of what's happening. It helps us to really have an idea when we're graphing a function to know what the parent function looks like. For example, the parent function y equals x cubed. We know what that parent function looks like. It's just the x cubed curve comes up, levels off, and comes up. It's got 3 key points on it that might help us out: 0, 0, 1, 1, and -1, -1. Knowing what y equals x cubed looks like, knowing its graph and maybe these 3 key points allows me to graph something more complicated, like y equals maybe x minus 3 cubed minus 2. Because this is a transformation of the main function. What happens outside the function is going to shift the graph vertically. So this is going to shift the graph down 2 units. What happens inside the function with the x, that's going to actually shift the grid in the background. So if I'm right here and the grid moves to the left, it looks like the graph has actually moved to the right, but my hand's not actually moving. But it gives the illusion that it's moving the opposite direction because the grid in the background is moving. So that's why when we see -3, the grid moves 3 to the left, which gives the illusion that the graph itself moves 3 to the right. That's why in parentheses, it's going to move the opposite direction from what we expect it to. So if I wanted to graph this function, it's 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. This center point of 0, 0 moves 3 to the right and down 2. That's now the center point. The bottom left of -1, -1 moves 3 to the right and down 2. It's here right now. This 1, 1, it moves 3 to the right and down 2. It's right here. And now the function's going to come up and bend and level off. And now it's this function over here. So that's kind of what happens when we have a transformation of functions. It's going to move based on that parent equation. So hopefully that helped get you started on those. We are going to continue working through to answer your questions. There are so many great questions coming in the chat. Keep them coming. We're going to answer as many of them as we possibly can. And one question I see is about elimination. So let's do some elimination. That is from TikTok. Harrison Carlson, I think, is asking that question. Let's do that. These are equations like 3x minus 4y equals 7 and 2x plus 2y equals 0, I think. Yeah. The idea of elimination is we want to get opposite numbers in front of either the x or the y. And it doesn't matter which one we pick on, you'll get the same answer either way. Sometimes one is easier than the other. In this case, it's probably going to be easier to get opposites in front of y, because you notice if I double this 2 and make this a +4, +4 and -4 are going to sum to 0. So I'm going to multiply this equation by 2. When I do, the first equation stays the same, 3x minus 4y equals 7. The second equation becomes 4x plus 4y equals 0. And now we've got opposite numbers in front of the y's, a +4 and a -4. The reason that's nice is we can add them together. 3x plus 4x is 7x, -4y plus 4y is 0, and 7 plus 0 is 7. So all I have to do to figure out what x is just divide both sides by 7. And when I do, I get that x is equal to 1. We've solved for x. Now all we have to do is figure out what y is by going back to either original equation and plugging this one into it. Let's go to the first equation for no other reason than it's on top. So we've got 3x's, which we said was 1, minus 4y's is equal to 7. Well, 3 times 1 is 3, minus 4y's equals 7. Subtract 3 from both sides. -4y equals 4. Divide both sides by -4. And y is equal to -1. So for our final answer, usually written as an ordered pair, x comma y, x is 1, y is -1. And that's going to be our solution using elimination, multiplying an equation by something so that we get opposites in front of either x or y. Great question. Thank you for asking about it. Another great question came up about distribution and another question about factoring. They're closely related. So let's talk about the distribution question. That came from Instagram at Philly Tay. We're going to talk about distribution first, and then we'll do the opposite of distribution, which is factoring, which is probably one of the most important skills that you learn in algebra and pre-calculus, is how to factor. So let's first start with the idea of distributing. First, we'll start simple and we'll kind of build up. Let's do 5x times 2x squared minus 7x plus 3. The idea of distributing is we can multiply this 5x by every piece inside the parentheses. It's going to go all the way across. So 5 times 2 is 10. And if I have an x times x squared, that's a total of 3 x's that are multiplied together. 5 times -7 is -35. And x times x, that's a total of x squared because they've been multiplied together. 3 times 5 is 15 times the x. So that's the idea of distributing, is you take this thing in front and it goes on to each term. Now, there's no reason that it just has to be one thing, though. I might have something like 4x minus 7 times 3x plus 2. And I can do the distributing here as well, exactly the same way. We're going to take this 4x and it's going to distribute onto both parts past the parentheses. 4x times 3x is 12x squared. 4x times 2 is 8x. But we're also going to take this -7 and it's going to distribute onto both parts. -7 times 3x is -21x. -7 times 2 is -14. Then the only thing we have to do to kind of clean this up and finish it is look for any like terms. And sure enough, we have like terms in the middle that we can combine. So we have 12x squared minus 13x, 8 minus 21, minus 14, and we get our final solution. But wait, there's more. It's not an infomercial, I promise. Although if you follow Chad, we'd really appreciate it. But this can be really extended on to more complicated problems. Like if I have 2x squared minus 5x plus 3, and I want to multiply it by 4x squared minus x plus 6. Well, all we're going to do is take each one of these terms and distribute it onto the parentheses. So I can take this 2x squared and multiply it by the 4x squared. That's going to be 8x. 2 and 2 gives us to the 4th power. 2x squared times -x, that's going to give me -2x cubed. And 2x times the 6, that's going to be 12x squared. Okay, we've distributed the 2x squared through. Now we're going to do the same thing with the -5x. -5x distributes onto the 4x squared, giving us -10x cubed. -5x distributes onto the -x. That's going to give me +5x squared. And -5x distributes onto the 6. That's going to be -30x. But wait, there's more, like I said. We've also got this 3. So the 3 is going to distribute. 3 times 4 is going to be 12x squared. And 3 times -x is going to be -3x. And 3 times the 6 is going to be +18. And so in this way, those colors look really similar. They're different colors, I promise. In this way, we distribute through every term. And now all I have to do is look for like terms. This guy has a 4th power on it. There's no more 4th powers, so 8x to the 4th is in my final answer. Let's look for cubes. -2x cubed, -10x cubed. That's going to give me -12 of these x cubes. Let's look for squares. 12x squared plus 5x squared plus 12x squared. That's 24 plus 5 is 29. 29x squared. Looking at x's, -30x, -3, that's -33x. And finally, we've got the +18 at the end. And that's what we get when we multiply this out. And it's really that same concept that we did in that very first problem where we just distributed. This is just doing it a lot more times. It's not any more difficult. There's just doing it a lot more times. And so that's distribution and how it works. And then it leads into doing this process in reverse, which is factoring. And I see that Sage Spam 8 from Instagram was asking about factoring. So let's do some factoring. There are lots of ways to factor, and I don't care which method of factoring you learn and master, as long as you learn and learn one of these factoring methods. Some people like the box method. Some people like the AC method. Some people like the lattice method. Some people like the grouping method. There are lots of different methods to factoring. My personal favorite, I call it divide and slide. Let's do 6x squared plus 7x minus 3. Did I say divide and slide? I meant slide and divide. We slide first, divide second. Let's look at how that works. The idea of slide and divide is I'm going to slide this 6 over to get married with the 3 to make life easier. So 6 times 3 gives me negative 18. So it's not there anymore. I have x squared plus 7x minus 18. This blue equation is going to be easier to factor than the black equation, but the answer will help me find the factored form of the black equation. Here's how. This is going to factor x squared is x times x. We need two numbers that multiply to 18 and add to 7. 18 is 9 times 2. If the 9 is positive and the 2 is negative, that will give me the 7x in the middle. So we did the slide with the 6. To get something easier to factor, now we divide with the 6. I'm going to divide both of these numbers by 6 and reduce these fractions. 9/6 reduces to 3/2, and 2/6 reduces to 1/3. These denominators are what need to go in front of the x's. So I've got 2x plus the 3 and 3x minus the 1. And this then is the factored form of the original equation up on top in black. Excellent. So hopefully that helps with your factoring problems. This method works on all of them. They don't even get any more complicated. The numbers might get bigger, and so you might need to do a little bit more work to find the pair of numbers that multiplies to the negative 18 and adds to 7. But that's pretty much all there is to factoring. Just got to get used to it, which means you need to practice. You need to do lots of problems. Never can do enough factoring problems. Factoring does not go away in math. There's a lot of students who are like, gee, I don't need to learn that method. I'll just kind of slide by on this chapter, and then the next chapter, I don't have to worry about it anymore. Factoring never goes away. It comes up in trig, it comes up in pre-calc, it comes up in calc, it comes up in differential equations. It never goes away. Take the time to learn how to factor. It will pay off, I promise. Chloe Webb on TikTok is studying special ed at Ball State. Good major to go into. Lots of jobs. It can be very rewarding. The difference that you're making on some people, that is really, really great. But you're asking specifically some reasoning methods with the quadratic formula. I think you just want to see an example of the quadratic formula is what I'm interpreting from your comment. If you want more, maybe you could clarify in the comments as well. But the idea with the quadratic formula is if I've got a problem that I am trying to solve that's equal to 0, we would first try to factor it, right? So I might try the slide and divide. I slide the 5 over and I get x squared minus x minus 5. I'm looking for two numbers that multiply to -5 and add to -1. The problem is -5 is 5 times 1, and that's it. It's prime. We're stuck. There's nothing with 5 times 1 that's going to get me to -1, so I cannot factor this problem. We call it prime, and so we're stuck using the quadratic formula. The quadratic formula tells us the answer for x is the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. It's a formula you need to practice and memorize. If you're going into education, learn a song that teaches the quadratic formula so you can teach your students the songs. Do you like Mary Had a Little Lamb? Then sing Mary Had a Little Lamb. X is equal to the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. If you like Farrah Jacques, opposite of b plus or minus the square root of b squared minus 4ac all over 2a, all over 2a. Learn a song that makes the quadratic formula fun and easy to learn for your students, and it will help you remember it. So let's plug in our values. Remember, a is the number in front of x squared, b is the number in front of x, and c is the number without an x. Now, you do not use the x's when you plug in. You just use the numbers in front. So for this equation, x is equal to the opposite of b. Opposite of -1 is a +1, plus or minus the square root of b squared, which is -1 squared, minus 4 times a, which is 5, times c, which is -1, all over, including the 1, all over 2 times a, which is 5. And then it's just a matter of simplifying this expression. So we have x is equal to -1 plus or minus 4 times 5 is 20. A negative and a negative makes a positive 21. So we have the square root of 21 all over 2 times 5, which is 10. And that is our solution using the quadratic formula. For those of you that are just joining us, welcome to Cheg's Office Hour on Pre-Calculus and Algebra. We are here every week to answer your algebra and pre-calc questions. So continue to come with those questions. Make sure you're scanning this QR code over here in the corner because it's going to keep you up to date on the schedule so you can see what we are doing and when, so you make sure you don't miss future lives. All right, great question coming in from Instagram. It is SpideyBitu2706. How do you draw a graph of, and we have an equation. Let's look at how we can draw that graph. There's actually several ways. Let's see what important information we can pull off of the graph of y equals x squared minus 4x plus 5. And maybe I'm going to stick it over here. Okay, we're going to graph it over there based on everything we learned. First thing that I'll look for when I'm making a graph is what are the x and y intercepts. To find an intercept, we make the other variable equal to 0. So if I want to find the y-intercept where it crosses the y-axis, I make x equal to 0. So for the y-intercept, I make x equal to 0, which becomes 0 minus 0 plus 5. So the y-intercept then is the 5. It's this number off the side. So if I come up 5, 1, 2, 3, 4, 5, that is my y-intercept right there at 5. If I want to find an x-intercept, to find an x-intercept, we make the other variable equal to 0. So we'll make the y equal to 0. So 0 is equal to x squared minus 4x plus 5. This is a factoring problem like we just got done talking about. So let's factor this expression. It becomes x minus 5. It's not going to factor. Did I write it down right? Minus 4 plus 1 is not going to factor. Well, that's a bummer. It looked like it was going to factor, but it only would factor if that 5 was negative. We could use the quadratic formula. We just talked about the quadratic formula where x is equal to the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. So we have 4 plus or minus. This is where it gets interesting, though. 16 minus 20 is negative 4. We can't take the square root of a negative number. Since we can't take the square root of a negative number, well, there is I. If someone wants to talk about I and complex numbers, stick it in the chat, and I'd love to talk about complex numbers. It's a great topic in pre-calculus as well. But in terms of the graph, there are no x-intercepts, so we're out of luck for that one. The other piece of information I might be interested in, though, is the vertex. And the vertex is literally the first part of the quadratic formula, the opposite of b over 2a. We don't do the plus or minus square root part, just the opposite of b over 2a. So for this problem, the opposite of b, the opposite of negative 4 is positive 4 over 2 times a, which is 1. The x-coordinate, 4 divided by 2, is 2. That tells us the x-coordinate. To find the y, we just have to plug it into the function. So y is equal to 2 squared minus 4 times 2 plus 5. 2 squared is 4 minus 8 plus 5. 4 plus 5 is 9 minus 8 is 1. So x is 2, y is 1, that is my vertex. So let's go 1, 2, 3, 4. So that we can say x is 2, y is 1, there's the vertex. And what's nice about parabolas is we know they're going to be symmetrical U-shaped curves. So if I go over 2 and up 1, 2, 3, 4, I should be able to go over 2 and up 4 to get kind of another point on there. And now we can graph that parabola, and sure enough, there are no x-intercepts like we expected because we weren't able to factor or solve the 0 equals equation. So that is how I would factor and solve it. A question came up though, why when I was trying to factor could I not use -5 and +1? Because -5 and 1 does equal -4. That is true, but if I were to multiply them together, they're not going to equal a +5. Because of this positive here, we needed to have a positive and a positive, or a negative and a negative. We can't have one of each. Dropping my pens. Got it. We're back in business now. Let's take a look at another one of your questions, because this is your office hour with Chegg. Excellent. I never took AP Stats. Good question. I love teaching stats, though. It's a fun class. From Instagram, we've got @SydneyB311 wants to know about polynomial long division. Let's do polynomial long division. We're going to do it 2 different ways. One way is probably the way you're taught. The second way is going to be a really cool shortcut if you've never seen it before. So let's say we're going to take the polynomial x cubed minus x plus 2, and we're going to divide it by x plus 4. Polynomial long division says we're going to take this x plus 4, and we're going to long divide it into this thing. Be very careful, though. When we put it in here, we need to account for every power of x. We've got x cubed, but you notice we're missing x squared. So we're going to do a plus 0x squared to kind of make that work. So we've got 1x cubed plus 0x squared minus x plus 2. That way all of our place values are accounted for. And long division is actually going to work exactly like you learned long division back in grade school. We're going to take this front digit of x cubed and we're going to divide out an x. When we do that x cubed divide out an x, we're left with x squared. Then we multiply that number by what's out front. X squared times x is x cubed, and x squared times 4 is 4x squared. Then what we do is we subtract that result. So I'm going to subtract it, which is going to change the sign on both of these, giving me x cubed minus x cubed is 0. 0x squared minus 4x squared is negative 4x squared. Bring down the next digit, which is the negative x. And we're going to do that process all over again, where I'm going to take this negative 4x squared and we're going to divide out an x. When I do, I'm left with negative 4x. Multiply the negative 4x times x, we get negative 4x squared. Negative 4x times 4 is going to be negative 16x. Then remember, the important rule that we're not going to forget is we're going to subtract this, which is going to change the signs, making it plus and plus. So that negative 4x squared plus 4x squared is 0. And negative x plus 16x is 15x. And we bring down the next digit, which is a plus 2, so that we can do that process again. One last time, taking the 15x and dividing out the x leaves behind a positive 15. So we'll do 15 times x, that's 15x. 15 times 4, that's 30. Mental math, almost made a mistake there. And then we subtract it, making them both negative, because 15 minus 15 is 0, and 20 minus 30 is negative 28. So we're going to say this has a remainder of negative 28 because there's nothing else that we can bring down and divide out the x. That's long division. That's probably the way they teach you the long division in class. There is another method, though, that's called synthetic division that makes this process easier and will give us the exact same answer for our quotient. The idea is we're going to take this denominator and set it equal to 0. And when we do, subtracting 4 from both sides tells us that x is negative 4. I'm going to put negative 4 over here in a box, and then across in front of the box, I'm going to put the coefficients of these numbers. We've got 1x cubed, 0x squared, we still need that, negative 1x, and then the constant 2. Leave a row of space, and this is where it's cool. All of this work is going to be summarized in a quick result. First, bring down the first number, bring down the 1. We're going to multiply 1 by the number in front and get negative 4. Add the 0, we get negative 4. Then negative 4 times the number in front is 16. Add the row to get 15. 15 times negative 4 is negative 60. Nope, it's 30. 15 times 4 is 30. Mental math sometimes gets you. Negative 30 and 2 is negative 28. The last number I'm going to stick in a box because the answer is going to be 1x squared minus 4x plus 15 with a remainder of negative 28. And notice that's the exact same answer we got up here, doing it by long division. A great question, though, came up from Brian Cruz while we were working that. Where did the 0x squared come from? The 0x squared is hidden in the problem, and if you forget it or you miss it, it's going to make everything else go bad. When we do long division, you have to account for every power of x, counting down. So if I've got an x cubed, I need x cubed, squared, first, and 0 power. If there is no squared, or if one of them is missing, you need to account for 0 of those. That way it works. Can you always use synthetic division? Synthetic division works great when you've got a linear equation here. Good question, Zabadi on TikTok. When we've got a linear equation here, which means there's no exponents. There is a way to do synthetic division with x squared. It's just a little bit more involved, and I think the long division probably gets you there just as fast. But if it's just the x plus 4, the synthetic division will give you the same answer. Now, with a caveat and a warning, if your instructor says you need to use long division, probably not going to take the synthetic division. They need you to show both methods. But it's a nice shortcut that can be helpful. Great questions. So many great questions. Let's see. We've talked about quadratics already. How do you factor a quadratic with a is greater than 1? That's going to be the divide and slide method. Should we do another one of those? I don't think you can ever do enough factoring problems. So what I don't like is a lot of schools and a lot of programs teach that you factor when a is 1 this way, and when a is not 1, you factor that way. And they have 2 different methods. That's terrible because you're doing the exact same thing. You're factoring. So why don't we have just one method? And I agree 100%. That's why I'm a big fan of slide and divide. We already did one problem, but let's do a different problem with slide and divide. Let's try 5x squared minus 19x plus 12. Okay. The idea of slide and divide is I'm going to slide this 5 over here and multiply by 12 to get plus 60. And then with the 5 out of the way, it's now x squared minus 19x plus 60. This equation now has a equal to 1, and it's going to be easier to factor. Now, when we factor this pink equation, it's not the answer to the black equation. It's the answer to the pink equation. But it's going to help us find the answer to the black equation. I'm looking for 2 numbers then. We've got the x's. That multiply to 60 and add to 19. 60 is 15 times 4. And if they're both negative, negative times a negative is a positive, and they're going to add to negative 19. Now, this blue line is the answer to the pink problem, not the black problem. How do we get the answer to the black problem? Here's how you did it. Remember that 5 we slid? Now we're going to divide it out. We're going to divide both of the numbers by 5 and then reduce those fractions. 15 over 5, that reduces to just 3. No more fraction. That's nice. 4 over 5 doesn't reduce, but because we have a denominator, the denominator is going to go in front of the x. So we've got x minus 3, and then this denominator, 5, in front of the x, minus the 4, and now it is factored when a was greater than 1. Great question. Great question. Factoring is so important, so it's definitely worth going over and over and over again, answering as many questions as we can. Excellent. So a lot of great questions coming in. Somebody wants to talk about Pascal's triangle expansion. That's an interesting question to take a look at. Let's go ahead and play with Pascal's triangle expansion, shall we? So the idea of Pascal's triangle expansion is it helps us do things like if we've got 2x minus 1, and I want to take that to the 4th power. One way you can do that is you can write 2x minus 1 times 2x minus 1 times 2x minus 1 times 2x minus 1, FOIL, excuse me, big sneeze. FOIL out the first two, get an answer. FOIL it out with the third one, get an answer. FOIL it out with the fourth one, get an answer. That's exhausting. Don't want to do that. Way too much work. Pascal's triangle. Pascal's triangle tells us exactly how to solve it. So the idea of Pascal's triangle is we're going to start with a 1, and then we're going to expand out from that with 1s down the edge. So if I expand out with a 1, but these two 1s are going to combine and add together to give me a 2, and then we add a 1 on the edge. A 1 on the edge. These two together add to 3. These two together add to 3, and a 1 on the edge. This third row here with the 2, that tells us how we're going to expand something with the 2nd power. The 1 with the 3, that tells us how to expand something with a 3rd power. We have a 4th power, so we'll go again. 1 and 3 make 4. That means this row is going to tell us how to do a 4th power. 3 and 3 makes 6. 3 and 1 makes 4. And we do a 1 on the edge. These numbers tell us how we're going to multiply out a plus b to the 4th power. We put the number 1 in front of the a to the 4th power. Plus, we put the number 4 in front of, now the a's are going to count down, so it's going to be a cubed, and the b's are going to count up. Now there's 1b. Plus a 6, and the a's count down to 2, and the b's count up. Now it's b squared. Plus a 4. A's count down to 1, b's count up to 3. Plus a 1 in front of a's count down to 0, and b's count up to 4. And so this is the formula for a plus b to the 4th. We just need to clearly identify that a is the first term, which is the 2x. And b is the second term, which is the -1. And so we've got a formula now for a 4th power. We just have to plug in what we know. So a to the 4th is 2x to the 4th plus 4 times a, which is 2x cubed, times b, which is -1, plus 6 times a, which is 2x squared, times b, which is -1, plus 4 times a, which is 2x, times b, which is -1 cubed. I forgot the squared over here. Don't forget your exponents. Plus b, which is -1 to the 4th power. And now we just have to simplify this expression to figure out what 2x minus 1 to the 4th power is. 2 to the 4th power, 2, 4, 8, 16. X to the 4th plus 2 to the 3rd. Oops, not plus. Because we're going to have a positive times a negative. It's going to make it a negative. 2 to the 3rd is 8. 8 times 1 times 4 is 32. X cubed. Plus, this one is positive because -1 squared is a positive 1. 2 squared is 4. 4 times 6 is 24. X squared. Plus, oops, actually it's going to be a minus because 3 negatives makes a negative. 4 times 2 is 8x. Plus, -1 to the 4th is 1. And this expression is what 2x minus 1 to the 4th is, using the Pascal's triangle. This is called Pascal's triangle because it's in the shape of a triangle, and it helps us multiply out binomials really fast? So that is a great question. Let's see. Ooh, we got some great trig questions coming in. Unfortunately, we're going to talk about trig during the trig office hour, so I'm going to have to hold off on those questions. Come back for our trig office hour. By the way, if you scan this QR code here, you can get the full schedule of when all of our lives are. With Chegg, we've got lives about trig, pre-calculus, calculus, economics, chemistry, physics, all sorts of subjects to help you be successful. So make sure you are logging in and checking those out. I think from Instagram, murateledits.math is wanting us to factor a pretty big one. Are we up to the challenge? Let's see if we can do this one. This one might not be as quick, but I think with a little guess and check, we can figure out the answer. You want us, I think, to factor 7x squared minus, I think you mean 33x. Plus 85. I'm going to make sure we can actually factor that first before we spend time trying to find the factors. I want to make sure I'm answering the correct question. No, that one doesn't factor. So I'm not sure what you want to do with that equation. Yeah, not sure what you want to do with that one. So we're going to have to skip it, unfortunately, because it does not factor. So maybe you could clarify in the comments what you want to do. Instead, we're going to go to an Instagram question from Kaylee Red 28, who wants to talk about inverse functions between the exponential and the log. Logarithms are so important in pre-calculus. We usually spend a significant unit in our pre-calculus and algebra classes on logarithms, and that's because they are the inverse of a log. The idea is we've got some base, and that base is going to be risen to some exponent. See how I did that? Exponent, it's an x. And then that's going to equal some answer. I'll use A for answer. So B is the base, X is the exponent, A is the answer. The idea of a logarithm is we're going to write this exact same function in a different way, but representing the same information. But instead of making it equal to the answer, we want it to be equal to the exponent, because a logarithm is an exponent. A log is an exponent. That's the most important thing you need to know. A log is an exponent. So when I write log, the log needs a base. What's that base going to be? Well, that base is going to be the same base as the problem, base B. And then inside of the log goes the answer. And then it's going to be equal to the exponent, because the log is the exponent. This relationship is important because some problems are really difficult to solve as an exponential, so we change them into a log. But some problems are really difficult to solve as a log, so we change it to an exponential. When we change forms, usually it makes hard problems into easier problems. So let's see if we can do a problem that does exactly that. Let's say I want to know 2 to some power 3x is going to be equal to 17. Well, how do we get that exponent out of the exponent and figure out what x is? How do we actually solve for x? Not really a clear way to do it. So let's rewrite it as a logarithm. We're going to do a log where the base of the log is 2 and the input to the log is 17. And that's going to equal the exponent of 3x. By writing it as the inverse, we get just 3 times x, and we can solve that for x quickly by just dividing both sides by 3. And then x is equal to the log base 2 of 17 divided by 3. Now, hold on, wait a minute. How do I put that in my calculator? My calculator cannot handle a log base 2. Great question. So what we do is we have another nice property is that if I have to log with some ugly base of a that we don't like, of b, I can change that base to be any base I want. And there is a log base 10 button on your calculator, so we can do a log base 10 of the same b as long as we divide by the log of that base of the old base. So on this one, the log base 2, we can change it to a log base 10 of 17 if I also divide by the log base 10 of 3. And that's going to equal the same value. Now, something to be careful of on your calculator, usually when you type log, it's going to open a parentheses. So make sure you close the parentheses at the end of the log. Same thing in the denominator. Something else to watch out for as you put in your calculator, though, is if you have multiple things happening in the numerator or denominator, you probably need an extra set of parentheses around those. So I would put that in my calculator exactly like that, and that's going to give us our solution. So the exponential can change into a logarithmic to make it easier to solve. All right. I had hinted a little bit at imaginary numbers, and Brian wants to talk more about imaginary numbers. So let's dive into a conversation about imaginary numbers. Imaginary numbers are where things get really kind of weird, because we give you all these rules about functions and how they work and domains and things that are allowed and aren't allowed. You can't, for example, take the square root of a negative number. That's not allowed. Well, we kind of lied to you. You can take the square root of a negative number. We just need to assign it something where all of math still works. It still has an inverse. It still has an additive inverse, a multiplicative inverse. It's closed on addition. It's closed on multiplication. All these rules. As long as all those rules still apply, and there's no ambiguity, we can break the rules. And so what we do is we take the square root of -1 and we define it as I. And that I represents the square root of -1. Now, actually, what we really did is we said -1 is equal to I squared. And so taking the square root of both sides gives you this relationship. But it's probably easier to think about I is the square root of -1. What's nice about this is it gives us a way to actually work with complex numbers that have square roots of negatives in them. So for example, if I wanted to do the square root of -20 plus the square root of -5, we can actually add these radicals by simplifying them. We're going to break the -20 down into its pieces. There's going to be a -1. -20 also has a 4, and -20 is a 5. So -1 times 4 times 5 gives us -20. What's nice about this is I can take the square root of -1, that's I. I can take the square root of 4, that's 2. Can't take the square root of 5, it's left under the radical. Now -5 I can break up into two pieces, a -1 times 5. We can take the square root of -1, that's I. We can't take the square root of 5, it stays under the square root. But what's nice about what we ended up with is we actually have like terms. We've got I root 5 on both of these, so we can add them together. We had 2 of them, we add 1 more, now we have 3 of these I root 5s, and we have found a solution for adding those together. What's really cool, if you've got some time to go onto Google tonight and you're bored and you want to do a neat search, or on Instagram or TikTok or wherever, complex numbers lay the foundation for what we call fractals. And so if you want to go out and look at some beautiful pictures that are made by a mathematical equation, search fractals, like the Mandelbrot set, the Julius set. Those are special fractals. And they are beautiful, colorful pictures that are actually built by this number I happening over and over again multiple times. It's really cool to look at the pictures. You don't have to understand the math to appreciate the beauty of the pictures. So take a look at that. Elena on TikTok wants to know about perfect square factoring. I think that's a great topic to take a look at next, because we talked a lot about factoring today, probably because it's one of the most important properties, skills, tricks, whatever you want to call it, from algebra and pre-calculus, that you can factor. But sometimes things factor to perfect squares. And to really understand what's happening with the perfect square, first, let's look at going from the perfect square to the unfactored form. And then let's see if we can go backwards and notice what's happening with the pattern. Because if you understand what's happening with the pattern, it's a lot less to memorize. I don't like to memorize. I like to understand what's happening, so I have to remember less. I've got a terrible memory, but if I understand what's happening, I don't have to remember. So squaring something, what that means is we're going to multiply it by itself, right? Anything squared is that times itself. And we know that we can multiply this out by taking a times a. That's going to give us the a squared. A times b is going to give us an ab. B times a gives us an ab. And b times b gives us a b squared. If I combine the like terms in the middle, we get a squared plus 2ab plus b squared. Now, often you'll see people say, don't go through all this work. Look at this neat shortcut. Going straight from the problem, I can square the a. Then you can multiply them together to get ab, and you double it because it happens on the top and the bottom. ab and ab is 2 ab's, and then you can square the b. A squared plus 2ab plus b squared, same thing. If you're doing this trick, you cannot just do a squared and b squared. You lost their middle name. The middle name is really important to this function. A squared plus b squared is wrong. You need that plus 2ab in the middle. Okay? So because of this relationship, though, it's really easy to take a problem like 4x minus 7 and square it. Because all I have to do is square the 4 to get 16x squared. Multiply these together to get negative 28x, and it's there twice. So negative 28 and negative 28 is negative 56x's. And then square the 7 to get 49. It's really easy to multiply it out. Okay, you asked about factoring, and I haven't done any factoring yet. Wallace, what are you doing? Well, understanding this is what makes perfect square factoring so much easier. Because if I've got 9x squared minus, let me see. I'm going to have a plus 4 at the end, making up this problem on the spot here. 2 times 36, 12 times. There, okay. I want to make sure it's a good problem. When I'm factoring, I might think, okay, we're going to do the slide and divide. 36, multiply to 36, add to negative 12. You can do that and it will work. But if you're keen enough to notice that we can take the square root of 9x squared, that's 3x. And we can take the square root of 4, that's 2. And then if you double it, multiply them together and double it, remember that middle term was always 2ab. If I can double it, then it's going to factor really nicely. 3x times 2 is 6x times 2 is 12x. If that matches the middle, then you're done factoring with the 3x and the 2. Just take the sign from the middle, and that's your perfect square completely factored. Well, I have had a blast solving these algebra questions with you. So many questions coming in. I couldn't get to all of them. I did my best to get to as many of them as I could, but we are out of time. So I want to give you a huge thank you for joining us today. Your engagement has been amazing. Questions have been great. It's been a pleasure sharing my love of algebra, pre-calculus, and really mathematics with you, and hopefully made it a little more enjoyable for you. Before you go, though, don't forget to check out chegg.com if you haven't already. Scan this QR code in the corner so that you can make sure you know when our live events are. Chegg is live almost every afternoon for several hours doing lots of different subjects. So if you have questions, there's probably a Chegg office hour to help you be successful. We're here with 24/7 support for all of your toughest subjects all semester long. Also, of course, make sure you follow Chegg here on TikTok, YouTube, Instagram, Twitch. Follow me as well. I'm at Wallace STEM. I'm also on TikTok and Instagram. Follow me there. Remember, we're here every week. Until we see you again, happy studying, everybody. It has been